Going back to cutaneous versus kinesthetic information, let's look at specifically what we mean by these definitions. For when I say cutaneous, I mean things that are related to the skin, and when I say kinesthesia or proprioception or force, I'm thinking about end organs that are in the muscles, tendons, and joints, things that are stimulated by bodily movements and forces. And what we'll do when we talk about the details of human haptic sensing is first discuss cutaneous and then kinesthetic types of sensing. The types of sensing are actually even broader beyond that, though. As I mentioned, we'll talk about tactile. There's different types of tactile senses or properties of the environment, which you might get through the tactile sense. And then in kinesthesia, there's muscle forces, or body and position movement, which actually can include both tactile and kinesthetic information. There's stereognosis, which we already talked about, which is really just the ability to understand 3D shapes, which is very related to kinesthesia. The last couple here, which are pain and temperature, sometimes people classify them as haptics and sometimes not. They're not really classic haptic sensing in the same way that mechanoreceptors or proprioceptors are, but they are forms of touch in a way that people do sometimes lump in with haptic information. In terms of what these mean, SAPCRA, we'll get into those details later. Mechanoreception is the idea that you have sensors that are typically inside the body, inside the skin, and afferents means that they're providing information that will arrive in the brain. Sometimes you hear the words afferent and efferent, and the way that I remember them is that afferent information arrives at the brain and efferent information exits the brain. Mechanoreceptive afferents, then, are receptors, which are, or sensors that are in the body, which in this case are in the skin and will arrive at the brain. And in terms of knowing how they're defined, they can be classified by depth. If it's defined as a 1, it's closer to the skin surface. If it's a 2, it's deeper beneath the surface. You can also get mechanoreceptors as classified by rate of adaptation, either rapidly adapting, or RA, or slowly adapting, which is SA. And fundamentally, what is going on at a low level is that the nerve cells are going to be firing at a certain rate. If it's rapidly adapting, then it only fires when there's a big change occurring. So if a stimulus, say a pen coming up and pushing on the finger, occurs, then you'll get rapid firing on the onset of that stimulus. When the stimulus is being held constant, however, you won't get any firing from rapidly adaptive mechanoreceptors. And again, when the stimulus ramps down, you get some firing again. Slowly adapting sensors, however, will continually respond even when the stimulus isn't changing. However, in the long run, if the stimulus is on for a long time, as you'll see in a little experiment we'll do later, they will eventually not be responding because they do adapt, they're just adapting slowly. So if you see something that's an RA1 sensor or mechanoreceptor, then you can say that this is a rapidly adapting mechanoreceptor, which is close to the skin surface. Finally, people sometimes also classify mechanoreceptors just by the general sensing modality. I should say sensing modality. So what is the structure, the physical structure of the receptor? So let's get specific about this and talk about the 4 most, interesting cutaneous mechanoreceptors. I'm showing 2 pictures here. One of these is glabrous or non-hairy skin. The other is hairy skin. If you look at the palm of your hand, there's no hair there. It actually has a higher density of mechanoreceptors and is better for tactile sensing. Hairy skin, say on the back of your hand or your arm or your leg, doesn't have the same density of mechanoreceptors nor the same kinds, and so you don't actually have the same sensing capability there. I'm going to go now through each of 4 of the most important and interesting cutaneous mechanoreceptors and talk about their roles. The first one is the Merkel discs. This is used for form and texture perception and low-frequency vibrations. It's an SA1, so it's slowly adapting and it's near the surface of the skin. It's sort of shaped like a disc. It's near the border between the epidermis and dermis. And it responds to frequencies in a range that's fairly slow. So slowly changing stimuli can be sensed by these Merkel receptors. So pressure, as well as the form and texture and vibrations that are low frequency mentioned here, can be sensed by these receptors. Because they're near the surface of the skin, if your skin gets cold though, these receptors may not be active anymore. Ruffini endings are considered to be good for measuring static and dynamic skin deformation, or skin stretch. These are fibers inside of a sort of cylindrical capsule located in the dermis. They're slowly adapting, but they're deeper inside, so they're given a 2. And these respond at somewhat higher frequencies. And their stimuli are expected to be stretching of the skin or movement of the joints. Meissner corpuscles are thought to be good for measuring motion, slip, and grip, and more dynamic or fast skin deformation. They're rapidly adapting, so they're RAs, and they're near the surface of the skin. Again, they have lower frequencies, and you actually tend to see this pattern that the lower frequency mechanoreceptors are closer to the surface of the skin. So the type of stimulus that they respond very well to are taps on the skin. Finally, the Pacinian corpuscles, which some people classify as their own type called PC, or they say they're rapidly adapting 2. They respond to high-frequency vibration and can also respond to gross pressure changes. They're the deepest. They're very deep in the skin, and their frequencies that they respond to can be extremely high. So the stimulus they're good for is primarily rapid vibration. So the vibration feedback that you get from your phone, definitely activating Pacinian corpuscles. You can lay out some of these different receptor types on a chart like this and look at their different types, their general sizes. They're not insignificant in terms of their size. And you can look at what is their density. The diameter, I guess, of the Pacinian corpuscle, it's not that the actual size of each corpuscle is the size of the hand, but it tells you an idea of the range over which they can sense. So that diameter is not the actual size of the device, but the range of sensing that it has. The density tells you how many there are in the skin. And you can see the ones that are near the skin, they have to be more close together. They have to have a higher density in order to be able to sense contact, because the contact on the skin is very local at the top. They can respond to all of these different types of stimuli, as mentioned earlier, and so they have relative perceptual functions. So you can put them on a comparison chart like this. Now I want you to do a little exercise on your own to measure the frequency dependence of your receptors. So set up a little experiment where you lay a simple flat, say an 8.5 by 11 sheet of paper onto a very flat tabletop, and lay your hand over the edge of the interface between the paper and the table. You can move your fingers over this interface rapidly, and you can very clearly feel that there's an edge of the paper there. But then you should hold your finger still for at least 20 seconds and hold it as still as possible. And the sensation that there's actually, let's say, a really zoomed in view of this paper. Let's say here's your finger here. A really zoomed in view of this paper, let's say there's your paper, is here. After a long period, and in fact if I was really zoomed in, of course the finger would fill up all this space. After a very long period, you won't actually even feel the interface between the paper and the table. And that's because these mechanoreceptors are all adapting, and if the stimulus is no longer changing, eventually you won't feel it. So give that a try and see if you can feel the frequency dependence of your mechanoreceptors.